All right, guys, thank you so much. I checked with all of the groups, so you kind of noticed, yeah, that the two methods are the annihilator method. So on that second problem, which was a fourth order differential equation, we didn't learn how to do variation of parameters for fourth order equations. So that problem must be done using annihilators. I'm talking about number two. The first problem, we have a right-hand side that we don't know how to annihilate. So the first problem must be done with variation of parameters. So now you can see how I'm going to put it on the test without telling you what method to use, right? I'm going to give you something where you must use one method or the other because I want to see you demonstrate that method. So yeah, James.
Would you ever give us like a fourth order and then like a fraction on the right side?
Oh, something. If I gave you a fourth order one that you couldn't annihilate,
yes.
oh well, then I'm asking for trouble.
Okay.
Then I'm basically giving. Is this your? That giving you? Then I'm giving you a problem you can't do.
Right.
Right. At that point, yeah, the instructor probably needs to have their head examined. So no, it would have to be something that you could do one way or the other. Yeah, for sure. Yeah. Okay. Anyway, I just wanted to wrap up chapter 8 with that group work. During the break today, I know there were some problems on the sideboard earlier that got erased. We can put those back up from tonight's homework. I will try to save a little time to answer questions about the homework that's due tonight. Let me just remind you, that is, I think it's number 22, right? This one is due tonight. And if I don't have time to answer questions about it during class, which is possible, if that happens, then I'm going to rely on you guys to stop by my office hours, which is after my second class, all night tonight until midnight, with a quick dinner break at 9 o'clock. I will be around other than that dinner break all night. So if you have any questions on this homework that we don't get time to answer during class, you can bring them to me in office hours, either in person or in Zoom, whichever way is better for you. After that, our next homework, which is actually the second to last one of the semester, is due on Saturday. And so this one is going to basically cover the stuff we're doing this week. You can probably get at least half of it done by Thursday if you have time, because I'm going to cover 9.4 today, which is part of what that next homework is about. But there will be a little bit of it that you guys are going to have to do on a quick turnaround. I'm going to teach you 9.5 on Thursday, and I want to have you do those problems by Saturday. Normally, I would give more time. The reason I'm not, of course, is because we have a test. Next Tuesday, our midterm 3 is next Tuesday. And I've already kind of talked about what it's going to cover and all of that. There's a resources folder already posted with, as usual, a couple of sample exams and then a overview of the material, a packet that sort of says, oh, here's all the things you should be able to do. And like, here are all the important words and that kind of stuff. So I will leave that for you to take a look at in Canvas for now, so I can kind of just let that go. But that's in our immediate future. And then, believe it or not, 2 weeks from today, we're done. We have our final exam. I mean, it's going to be so fast how quick the semester is winding down. So the students who generally have an easier time of it here at the end are the people who take the midterm seriously, so that they don't have to spend hardly any time studying chapters 6, 7, 8, and 9 next week. They can focus more on getting caught up on the older material, which shouldn't be completely like starting over, because of course we keep doing determinants, we keep doing EROs, we keep talking about vector spaces and subspaces. So some of that older material should still be kind of percolating somewhere in there, not too far below the surface. But anyway, I really think the key to success is to try really hard to double dip on this midterm, meaning study really hard for this midterm so that you can reuse all that knowledge again on the final, which is the following week. I'll talk more about the final next week. I don't want to, in fact, I have a folder for the final as well, but I don't want to confuse everybody with too many different things at once. So I'm going to focus for now on getting us ready for the midterm. Okay, so that's kind of where we're at. What we need to do today is talk about the last couple of sections, and as I said, this will drift into Thursday as well. But I had started on Tuesday talking about section 9.4. And what this is, you know, the goal of kind of this whole chapter actually is to solve our linear system of differential equations. So now I'm changing gears. This is completely different than what we were just doing in the group work. But if I have x prime equals a times x, I would like to solve that for x. This is the goal in these next couple of sections, okay? And in section 9.4 specifically, we are going to be talking today about the situation when A is non-defective. So remember what that means. That's also part of this coverage of this midterm coming up. A non-defective matrix is just one where every eigenvalue holds its weight. And in other words, there are n, let's just assume this is an n by n matrix here. There are n linearly independent eigenvectors, okay? So I'm gonna restrict our conversation today just to the non-defective matrices. And then on Thursday is when we're gonna talk about what do we do about a defective system. So just to remind you, there's trying to figure out what time it is. Okay, just to remind you, the solution to this system, this was a kind of a exciting moment for me, at least last week, when we pointed out that it relies on the eigenvector pairs of A. So somehow the stuff we learned in chapter 7, if you were ever wondering, well, why do I care about eigenvalues and eigenvectors of a matrix? I'm going to give you a great reason to care about it in this section, right? Basically the idea of this section. So the solutions here, the solutions to this system form an n-dimensional vector space. That's one thing that we know. And it turns out they take the form. So this is really like a recap. I'm reminding you of what we did last Thursday. So we can write down the form of what these solutions look like. They're going to look like x of t. Remember, t is like representing time. And so this is a vector function, and it looks like this, guys. E to the lambda t times v. Okay, so everybody's going to need to know this. This is a really classic expression of the solution to our system. And this is simply, this is where lambda and v is an eigenpair of A. So those are eigenpairs of A, okay? Right, and if A is not defective, A non-defective, which is what we're assuming for today's talk, if the matrix is non-defective, then that means that we get n of these eigenpairs that are linearly independent, right? So we get n linearly independent eigenpairs, which would look like, you know, lambda I, comma, v sub I. So we can get all of these pairs in that fashion. And so that means that we get, this implies, I'm just going to switch over to this next board now. This implies then, guys, that we get n linearly independent solutions. Namely, x sub I of t equals e to the lambda I t times vi. There they all are. There they are. Now, you might pause for a second and just convince yourself, are these really Li? I mean, the eigenvectors are Li, but then are these Li? These are the actual solutions that are supposed to be a basis. Remember, I have an n-dimensional vector space, so I need n basis solutions. This looks like n candidates for solutions to my system, but I should technically, I'm just going to show you. Now, I'm not going to normally be asking you guys to do this unless I specifically say that I want you to check linear independence. We normally will kind of just skirt over that fact. But remember that our test is the W test, the Wronskian test that we learned about in the last couple of weeks. And how that W is defined, the way the Wronskian is defined, is we take the determinant. Just to remind you again, we take the determinant of the matrix that we get by, this is the chapter 9 Wronskian. This is not the one that you were just doing on the group work, where you'd have to take derivatives. This is putting these vectors directly into the columns of the matrix, and you don't have to take any derivatives at all. So the first column is just e to the lambda 1t times v1. That's the first column of my Wronskian matrix. The second column is e to the lambda 2t times v2, and we go dot, dot, dot like that all the way along. So the last column would be e to the lambda t times vn. So you just build up this determinant. Now, one thing you might remember about determinants, if you multiply a row of a matrix by a constant, it factors up the determinant by that same constant. So if I multiply the first row of a matrix by 5, then the determinant of the whole matrix will go up by a factor of 5. This was way back in chapter 3 when we were talking about the properties of determinants, and I made these comments. Oh, if you permute 2 rows, you pick up a minus sign. If you multiply a row by a constant, the determinant multiplies by that constant. Right? If I add a multiple of one row to another, nothing happens. See, right now we're reviewing for the final. Back to chapter 3, right? The properties of EROs, how they affect determinants. So it turns out that the similar properties are true for columns. So if I multiply a column of a matrix by 5, then the determinant of the whole matrix goes up by 5, by a factor of 5. Well, in this expression, guys, you might notice I have multiplied the first column of, if I imagine the v1 is there, and I've multiplied it by this e to the lambda 1 times t, that's like a scalar. It's a scalar function that's being multiplied into the first column of this matrix. So you could pull it out. You can pull it out. It's like if that was a 5, you could put the 5 out in front. And then in the second column, maybe you had an 8. You can pull that out in front also. So there's an e to the lambda 2t that gets pulled out as well. You end up pulling out all of these exponentials, guys. They all come out. They all come out. And the only thing that you're left with then that is not pulled out of the matrix is just this determinant of the vectors themselves. Okay, so I'm doing the W test right now. I'm checking my Wronskian here. And let's remember, if the Wronskian, do you remember the W test? If the Wronskian is not 0, then the vectors are Li. Okay. Can e to the lambda t be equal to 0? No, never, right? Doesn't matter what t is. If you have like e to the 2t or e to the 7t or something like that, doesn't matter what you plug in for t, it'll never be 0. This is not 0. And then neither is this one. And neither is any of these. None of those are 0. Okay, because those are exponentials. I mean, you just draw the graph of e to the x, right? It never crosses the x-axis. There's no roots to that equation. It's never 0. So you have all these non-zero scalars in front, and then you're taking the determinant of this. So this is a matrix that is actually an n by n matrix, and the columns of that matrix are Li already. The original vectors, the v1, v2, v3, and so on, they are already Li. So you're talking here, guys, about a matrix, a square matrix, whose columns are Li. Does that sound familiar? That kind of a matrix is better known as a, it's not the word I was looking for. A matrix whose columns are Li would have to be what kind of matrix? This is also a good review from chapter 4, actually. So you put these linearly independent columns down and you start doing EROs on it. Where are the pivots going to end up? Right down the main diagonal. Are there going to be any unpivoted columns? No, you will have pivots going all the way down the main diagonal. No free variables. No free variables at all means that your columns were Li to begin with. Actually, the word I was looking for is that the matrix is invertible. It is an invertible matrix. When its columns are Li, it is an invertible matrix. And we know that an invertible matrix has a non-zero determinant. So guys, all you're doing here is multiplying a bunch of non-zero things together. And therefore, at the end of all of that, your result should be non-zero. And that checks the Wronskian test, right? So we do have linearly independent solutions here. There's n of them. And so they form a basis. And if they form a basis, then that means I can write down, in fact, I'm going to do that next. So let's just write down, first of all, the set x1, x2. These are vectors, guys. Be sure if you're taking notes, be sure to put arrows on the top of things that are vectors. So these are vector functions. That set is Li, hence a basis of solutions. The basis has to be Li, and it has to span the space. And that is true about these functions. And so, guys, if they span the space, we can write down our general solution. The general solution will look like the following, guys. X of t equals C1 times e to the lambda 1 t times v1 plus C2 e to the lambda 2 t times v2 plus dot 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 plus Cn e to the lambda times t vn. That's the final answer right there. That's the general solution to our system. It's exactly what we would have. Okay. So on Thursday last week, I did an example of this, but it was just a quick one and it was kind of small. I'm gonna put it back up on the board really quickly again, just again, kind of by way of recap of this. And the example was, just to remind you, you're going to solve x prime equals a times x, where A is the following matrix. So I'm just going to use the example that I used on Thursday last week. So it's just a 2 by 2. So we have this matrix here, -2, -7, and then on the second row, -1 and 4. Okay. And I am going to, in this solution, I'm going to skip all the details. So I'm going to tell you right away what the lambda values are. It turns out that 5 or -3. By the way, guys, be sure that you know how to test these. What if I was on the exam next week and I decided to give you one of the lambdas for free? Let's say I didn't tell you the second one. Would you be able to figure it out? In a heartbeat, right? Because they have to add up to the trace. The trace here is 2. So if I tell you that one of the lambdas is 5, then you can figure out immediately that the other one is -3. So this kind of stuff you want to be able to kind of work with those fun facts. So these are the lambdas. And then from each of those lambdas, we have to find a corresponding eigenvector. Now, by the way, there's no repeats here. There's no repeated lambdas. So I already know that this is a non-defective problem. And I just, again, we did this last time. I'm going to write down the vectors that coincide here. For lambda equals 5, the vector is -1 and 1. Again, I'm skipping the null spaces here. We've had a lot of practice with that. We're going to get more practice anyway. For the second vector, we have 7 and 1. Okay, so together we have created here two eigenpairs. And so from that, I can now write down the general solution immediately. The general solution, I think I can do it right here. Haha, we'll see. We'll see if I can fit it in right here. The general solution, I'm just gonna copy this, this formula, right? X of t equals C1 times e to the 5t times negative 1 plus C2 e to the negative 3t times 7 and 1. Wow. Really squeezed in there. Is that readable? Legible? Okay.
Do we have to repeat check of this one? Do we next on C1, C2,
Okay, so we learned in chapter 8 that when we're solving these nth order differential equations, if there are repeated roots, what we do is we stack x's. Of course, here we would be doing t's, not x's. So the question I get sometimes in chapter 9 is, if the eigenvalues did repeat, would I be stacking t's? The issue would be, the answer is no, you would not be. First of all, even if the eigenvalue repeated, as long as it still pulled its weight, we could still just write our answer this way with no stacking needed at all. Because if the eigenvectors, if the v's are Li, then even though the lambda was a repeat lambda, we're still good. The solutions are still Li, I don't have to stack anything. So that's one thing. Now, if the eigenvalue is repeated and it doesn't pull its weight, then you have to come back on Thursday so I can explain to you how to do it there. That's the situation of a defective system. The answer to it is not to just stack t's. It actually is a little bit harder than that. So we will leave you in suspense for 2 days on that part. For today, everything is non-defective. Yeah. Are we good with this? I actually like to draw a picture at this point. This isn't really in section 9.4, but I am going to ask you to make sure you learn this, which is I want to have a visual idea of something called a phase portrait. So let me talk about this. This I did not do on Thursday last week. So phase portrait for this system. What I'm talking about is I would like to graph the solutions to our system. And when I say graph my solutions, I hope everybody realizes there are infinitely many solutions here because there's any number of choices for C1 and any number of choices for C2. I can make a million different choices. I am going to draw a XY coordinate system. I'm actually going to label it with X1 of t and X2 of t. And I would like to draw a few of these solutions. As I said, there are infinitely many solutions right now. I cannot possibly graph them all, but I'm going to try to graph a couple of them so we can get a sense of what this system is like. Okay. Again, I'm just going to recopy this. I think it's too small for everybody to see it easily. So let me just recopy my general solution here. What I'm going to start with, guys, is I'm going to go ahead and try a value of C1 and C2. And the easiest value that I know is to make C1 equal to 1 and make C2 equal to 0. If I do that, I should get one of my infinitely many solutions to the system. Does everybody see that? So if C1 is 1 and C2 is 0, we just make a little table here, kind of draw it out. Then what is my x of t? Well, then all I have is e to the 5t times the vector negative 1, 1. And I would like to put that solution onto my picture. It's actually like something called parametric equations that you would have maybe seen in calculus. At any value of t, I can plot a point on my picture. For example, when t is equal to 0, e to the 0 is just 1, and I just get the vector negative 1, 1. So I'm going to plot that here. Let's draw some tick marks here. Get my setup of the coordinate system. Give yourself plenty of room, guys, to kind of draw this picture. Don't try to squeeze it into a little tiny corner. I want you to be able to see it really easily. At t equals 0, I'm gonna plot the point negative 1, 1. And what I'm gonna ask you guys now is what would happen to that point if t starts to increase? So at t equals 0, I have the vector negative 1, 1. But now imagine that you start your clock. The clock starts running, t starts increasing forward in time. What's going to happen to this expression? I have negative 1 and 1 that's being now scalar multiplied by a scalar that is growing with time, right? As e to the 5t grows, it blows up actually to infinity, right? So what's actually going to happen? Like at t equals 1, just to give you a quick idea, if t is equal to 1, then my vector is e to the 5 times the vector negative 1, 1, which is really negative e to the 5th, e to the 5th. Isn't that just somewhere like way out here? It's still on this same line, so to speak. It's actually a line. It's just been stretched far away from the origin, right? The way I want you guys to think about phase portraits, I want you to imagine that this is the surface of the ocean, and that at time 0, you have dropped a feather right onto the top of the water. And you're looking down and you drop that feather right there. And the question I want to ask is, where do the currents make this feather flow to as time goes on, right? So if I drop my feather right here and I use this equation and allow t to increase, time goes forward, what that feather is going to do, guys, is it is going to flow out towards infinity. And I'm going to put arrows even on my curve to show that. It flows out along that line, right? The ratio of the horizontal and vertical components is still in this negative 1 to 1 relationship. You see that? As t gets bigger, guys, you're simply taking the vector negative 1, 1 and scalar multiplying it by a larger and larger number, which just means that your feather is floating out to infinity along that direction. If you feel like doing the camera or doing the stopwatch in reverse, you can let t go towards negative infinity as well. You can go backwards in time. What is e to the negative infinity? Approximately. It's basically 0, right? E to the negative is like 1 over a huge number. Yeah. Well, so that basically means that as time, if you were to reverse time, your feather would be getting pulled back towards the origin. And if you went way back to the beginning and t goes to minus infinity, your feather would have been right at the origin. Yeah, so that is one solution curve. Go ahead.
Can your graph ever be anything besides a line?
Oh yeah, we're gonna talk all about it. We're gonna talk all about it. This is only one solution. I could make many others. I could choose C1 to be negative 1 and C2 to be 0. If I did that, what would my x of t be? Now my x of t has a minus in front of everything. So it would be minus of e to the 5t times negative 1, 1. Again, I'm going to drop my feather in at time 0. And I'm going to have 1, negative 1. It's actually going to be down here. Right? And as time increases on this one, this feather is going to go exactly in the opposite direction. This is a very unstable phase portrait. If Zach drops his feather right there, and I drop my feather right there, 10 minutes later, our feathers are going to be miles apart from each other, right? So it is very sensitive to where exactly your initial condition put that feather on this picture. Right. So far, so good? Let's draw another one. What if C1 is 0 and C2 is 1? Now I'm not going to see the first term because C1 is 0. I just have the second term, which is x of t equals e to the negative 3t times the vector 7 and 1. So where does the feather go at time 0? Seven and one, right? E to the 0. at time 0, we have e to the 0, which is just 1. So we just get the vector 7, 1. Let me plot that. 1, 2, 3, 4, 5, 6, 7, and 1 is right there. So I'm going to drop that feather right there. And now I'm going to ask you, where does the feather go? As time increases, where would this feather tend to flow towards? And we have e to the negative 3t. So it's e to the negative 3t. So as t gets bigger and bigger and bigger, what's that exponential function doing? It's shrinking down to 0, right? This time your feather gets dropped in at 7,1 on this ocean surface. And where does the current take it? It actually takes this feather and starts to pull it towards the origin, guys. It pulls it towards the origin. Now, technically, it never gets there. Technically, this never turns into 0, 0, but it becomes, you know, it asymptotically approaches the origin, right? And then let's do one more, guys. C1 equals 0, C2 equals -1. Now we have x of t equals negative e to the negative 3t times 7, 1. One more time, I'm going to plug in t equals 0 here to figure out where my initial point is. When I put in 0 here, the exponential goes away. I have minus of the vector 7 and 1. That would be 4, 5, 6, 7, -7, -1. Now you're dropping your feather over here. And again, because of the negative exponential, this feather is sucked in towards the origin. Now, what you have on the board so far, guys, is 4 solutions out of the infinitely many solutions to my system. And they are 4 different particular solutions that are based on 4 different initial conditions, right? Did you drop your feather here? Did you drop it here? Did you drop it here? Or did you drop it here? I have 4 different points I could choose to drop that feather. And in each of those cases, the feather is going to flow along the surface of the ocean. 2 of them, the feather comes together towards the origin. The other 2, the feather is going to float out to infinity. And the reason for that is really that one of my eigenvalues was positive and the other one was negative. That's why that happened. In a minute, I'm going to talk about, well, what would happen if they were both positive, or what if they were both negative? But I have one other thing I need to talk about first with the picture we already have on the board, which is, what if I drop the feather right there? Like, I could choose to do that. You know, that's my initial value. X of 0 equals whatever this is, you know, 6, 4, something like that. Right, so the question would be, what happens to that feather? Well, that's going to be some solution here with, you know, maybe messier values of C1 and C2. You can see that my C1 and C2 choices here were super clean, super easy, but there's many other choices that aren't so nice. And so maybe this initial value coincides with C1 and C2 choices that are not nearly as nice. But here's the idea. I don't want to get too deep into this. What basically happens is this feather, if you drop it right there at time 0, it's going to flow in a manner that is consistent with the lines that are already on the picture. So it's going to, but it may not be straight lines. So this thing is going to kind of go like this. It's going to come along the directions of the arrows that are already there. So you just kind of see the way the arrow, you have to draw the arrows on this big X that you have. You have to have those arrows there, and then that kind of helps you. Like, so if I drop the feather here, right, then this one is going to kind of bend like this. Okay. If I drop it here, I'm going to get a curve something like this. And I'm not looking for perfect pictures. Of course, you'd use a computer if you wanted to get a great picture of a phase portrait. I could drop the feather here and I'd get something that bends around like this. And how many of these do you need to draw? Well, there is no right answer. It's kind of just however many you feel you need to get a good visual of the phase portrait. But that, my friends, is a phase portrait for that system. And so what I'm going to make here is a quick note about these phase portraits. And I'm going to see how you feel about it. So this This is the surface of the ocean, and you drop something on the top of it and you let it float around according to the currents that are represented by the lines and the arrows on that picture. That's the way I want you to kind of think about it. So I think what you can see here, guys, is that depending on where you drop this feather greatly affects the trajectory of that feather. And in this case, guys, so let me just make a quick little summary on phase portraits. Oh, and I should mention, if this was a 3x3 matrix, it would not be a 2-dimensional picture. In that case, you'd be talking about a 3D picture, and you would have not just the surface of the ocean, you would have like the air currents flowing in a 3-dimensional in this room, for example. We're not gonna go there. So I'm not gonna deal with that. This is gonna be for 2x2 systems. So we will just call this a good enough analysis. Because it's a 2x2 system, guys, it means we're gonna have 2 lambdas, always, because it's a 2x2 matrix, so you're gonna get 2 lambdas. And here's the first bullet point. If you have the first lambda is positive and the second lambda is negative, then your phase portrait, we get what is called a saddle. You know, you guys all took like multivariable calculus, right? Did they draw like the level curves of a surface? This is where you like slice through the surface. This is the level surface picture of the so-called hyperbolic paraboloid, which is the one that I can never draw. I was saying maybe this is why they don't let me teach that class. The hyperbolic paraboloid is like the potato chip. It's very hard to draw the picture of it. But it's also, if you don't want to think of it as a potato chip, it's like a saddle that would be on a horse or something like that. And so if you slice through it horizontally, the cross sections look like exactly the curves that are over there. So just to tie it in a little bit with something you might have seen in calculus. But we'll call this case a saddle. Now, I want to pick your brain here for a minute, guys, to see, what do you suppose if both of the lambdas were positive? So if they were both positive, the question is, what would it look like? Maybe I'll steal a little room here to draw up a picture. Like, do you see the impact of the positive versus the negative? Right, the eigenvalue that was positive, which was 5, gave me this curve here and this curve here. And the important thing is that the feather is flowing out, away from the origin in that case. This phase portrait here, I'm going to draw a little mini phase portrait. The way this phase portrait is going to look on this second case is every single arrow in all directions is going outward. This is going to be like the rays of the sun coming out. I don't care where you drop the feather, unless you drop it right at the origin, which is like the trivial solution where the feather just sits there. If you drop that feather anywhere else, then guys, what do you have? You've got, e to a positive times t, and then c2 e to a positive times t. Everything's blowing up to infinity, right? So I don't care where you put the feather, it's going to go out to infinity, and we get what is called a source. That is called a source. A source is a phase portrait where all of the arrows are going out. The thing that's easy about this is that to figure out the different cases, you just have to know, are your lambdas positive or negative, one of each, or are they both positive? Or the third case here is, what about this? If lambda 1 and lambda 2 are both negative, we get what is called a sink. So on the case of a sink, I'm going to draw a little mini picture of that as well. In this case, here's my x1, x2 axes. For a sink, The feather is being sucked in to the center of this space portrait from every possible initial direction. So it doesn't matter because all of the exponentials have an e to, I mean, guys, if I give you C1 e to the, let's just make up some numbers here, negative 8t times something plus C2 times negative e to the negative 6t times something. I don't even care what's in these entries. As t gets big, the e to the negative 8t just basically sucks that down to 0, 0. And this one also gets sucked down to 0, 0. As time goes to infinity, doesn't matter where you drop the feather into your ocean current, it will be sucked to the origin. And it behaves just the way you think about a sink, everything getting sucked into the center of it. So this is kind of how the phase portrait would look in that case. Okay. Good enough? Make a little bit of sense? Okay. I'm gonna take a break in a minute, but I'm gonna put another problem on the board first, and you know how I do my soap opera style. I have to like get you to come back to hear the rest of the story. So let me throw another example on the board here, and then we will take a break in a second. Okay, so I just want to get this started. Unless there's any questions about these phase portraits. Feel okay with that? I've been known to make matching problems on the test. I'll give you, here's 3 matrices and here's 3 phase portraits. Match which matrix goes with which phase portrait. Super easy question because all you have to do is find the lambdas for the matrix. It's got to be a 2 by 2 matrix. Find the lambdas and then just figure out, oh, are they both positive? Are they both negative? Or is there one of each? And that's how you figure it out. That's pretty easy. Okay, but there's always a wrinkle. And I'm going to show you with this example what the wrinkle might be. Okay, so let's say I ask you to find the general solution to, so I'm going to write it like this, guys. X1 prime equals 9x1 plus 29x2. And then x2 prime equals negative x1 minus x2. So this is a linear system, a 2 by 2 system again. But what I've done here is I actually have not given you the matrix directly. I've actually written out the equations. But what you're going to need to realize is that it's no big leap to figure out what the matrix is. The matrix here, the matrix is just 9 and 29, and then -1 and -1. So you can go straight to the matrix from the system. But sometimes I like to write out the system just so we can kind of remember, you know, what are all the unknowns and how do they lay out. I don't like to just write down a matrix. It doesn't really show enough. So this is the system I want to solve. So I have to find the eigenvalues. And so that means I've got to do the determinant of the matrix that I get when I subtract lambda off of the main diagonal. So let me just do this one really quick, guys. We're not going to solve this entire example before we end up taking a break. But first thing I want to do is just get the first part started. Here's my 2 by 2. I'm going to use the 2 by 2 formula. So that would be 9 minus lambda times -1 minus lambda. And then minus -29 is actually a positive 29. Okay, and that's just going to be a quadratic equation. So I don't mind going ahead and multiplying this out. I'll have a lambda squared. Then I have -9 lambda and plus lambda, that's -8 lambda. And then I have -9 and plus 29, which is actually plus 20. And this is what I need to set equal to 0. And this one actually does not factor nicely. Of course, it does factor. We can always take a quadratic and get the roots by using the quadratic equation. So I'm going to do that here. So to get the lambda values, I take negative b, which would be 8, plus or minus the square root of b squared, which is 64, minus 4ac, which is 4 times 20, which is 80. And then this is all over 2, all over 2a, which is 2 in this case. And let me just try to clean this up a little bit. I have 8 over 2, which is 4, plus or minus, da, 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 da. Here's what I wanted to deal with today. This is the square root of a negative number. That is the square root of negative 16, which would be 4i, which is being divided by 2. So it's actually 4 plus or minus 2i. Oh my goodness. So we can, of course, find the corresponding. This is a good review, by the way, for the exam. This is chapter 7 all over again. But we have imaginary numbers. We can use the fun facts to check those, but I promise you, this is what they are. So we would then have to work with, I'll start with 4 plus 2i, and I have to do a little null space here. So let's just kind of remember how this works. This is only a 2 by 2. There's actually some in the homework. There are going to be 3 by 3s, but this is a good starting point. I have to write down a matrix where I subtract 4 plus 2i from the main diagonal of A. So I take A and I'm going to subtract 4 plus 2i. So the 9 will turn into 5 minus 2i. And then the 29 stays the same. The negative 1 in the lower left stays the same. But then I have a negative 1 and I'm subtracting 4 plus 2i. So it becomes negative 5 minus 2i. So I want to just remind you again, I'm kind of sounding like a broken record from chapter 7. These two rows have to be multiples of each other. Even if they don't look like it, the imaginary number has kind of camouflaged that, but they must be, because this matrix has a determinant of 0. With respect to this choice of lambda, we know we got 0 here. So this is not invertible. It means we must, if we did the EROs, which we're not, but if we did the EROs, we would get a row to 0 out. So I'm going to cross off either row in this case. I'll cross off the first row. And then I'm going to use my little trick that I taught you back in chapter 8 with 2 entries in a null space. If I have an A and a B sitting in a particular row, I can write down my vector by just swapping. So I take this thing and I just swap the 2 positions. And I do a sign change on one of them. I think I'm going to take the negative 5 minus 2i and make it positive, and I'm going to leave the negative 1 the way it was. And so what does this mean? I've got my, by the way, this is a non-defective matrix because there's no repeat lambdas. It's just that they're complex, but they're not repeated. So I can write down a solution now. And this is what it would look like. E to the 4 plus 2i times t times the v, which is the vector 5 plus 2i and negative 1. That would be it. That would be the answer. Except, of course, that this makes no sense. I wouldn't know how to plug numbers into it. I wouldn't know how to draw a picture of it. I could not explain that as a real answer to a physical problem in the real world to my boss. This would not be acceptable. So we have to figure out how to take this. This is so simple. E to the lambda t times v. I thought that was all I had to do. Yeah, except if there's imaginary numbers in here, we're going to have to work a little harder now because I don't like having imaginary solutions. So let's take 10 minutes and chew on that, or take a short break and chew on what are we going to do. And then after the break, so just leave your notes right where they're at. I'm going to give you a chance to decompress, and then we'll pick it up right at that step after we take a short break, and I'll come back and we'll finish this up. It's a little tricky. You're not going to want to miss it. So I'll give you a little break though first. Do you remember what the problems were that were on the board? Point 7, number 6, I think. And it was 9.3, number 5. I think what was there. I don't know if I'm gonna have time to get to them, to be honest with you. But we'll see. No, not 9.4. 9.2 is the other section.
It's a matter, yes,
Yeah, I'm not sure I'll get to it. I'll try, but it's already, I realize it's already 5:20. Questionable.
You raise 9.2, you could raise 9.2, make it like 3 and then by itself and. Just do and then A. There you go, now you can.
And put a minus sign, so it's problem -5.
Yeah. It's gonna be like just for- maybe, but-
I don't know why you're.
Nice. Thank you.
Good enough.
I'm happy.
Runs on this.
Yeah, that part, yeah, that's right.
What's the question?
How did we get the 5+2i and then the minus, we get to like.
So you take these two numbers.
Right.
This is your A and your B.
Oh, okay.
A and B, so remember how it works, you switch the positions of them, so you're gonna put this one first and this one second.
Okay.
But then, not only do you switch the positions, you also do a sign change, so I just wanna remind you, when you do this A, B thing, you end up writing down a vector, which is negative B and A. Do
Oh, right.
you remember that? It's from chapter 7.
Thank you.
You bet.
Yes.
Probability you're gonna.
We're expecting to an actual lecture.
For part of the class, I will be covering one last section for, it shouldn't take very long, usually it's
Get
30,
them
40
from the
minutes.
SOA.
And then if you're not gonna miss it.
No, I'm-
Okay, good, yeah, and then we'll review the second half. Yeah.
You know, like. Taking apart. Yeah. Yeah, we did counting.
Yeah.
Yeah, counting that and, but right now we're doing like double. Like what's the point of something, let's say. Science like study on.
She's like, oh, FaceTime. You can see it, you can see the flash because I take a picture.
She looks different.
I know. He's trying to climb out. I know.
I found. Like, it was like. hanging. I heard.
Separate rooms. Or you guys are here?
She was just in the room, I was like in the living room.
Like her nursery?
It's just.
Nope, sure.
Push.
They are, they get straight real quick. I know.
Because it was.
Sweet.
But like something on top of it.
Well, her crib right now is adjacent to the bed,
Okay.
so my kind of might walk a little
She's
bit.
like.
Yeah. Rail that's adjacent to our bed is the same height as our bed, it's not above it, it's good, so I'm like, I gotta.
Yeah, well, I think.
It's not quite there, but.
But they do become very strong.
Very,
I had no idea how to do that.
Oh. Last time was rough too, I think she's just on the side. She just came out to no, it's just because she's now learning how to like kind of climb her crib, so it's just like. Period.
Yeah, it's
And my,
tiring.
I think it's the dichotomy, it's not like, man. I want that you're, and then I'm like, I don't want to put her in her nursery.
Yeah, I have one.
Right, it's not-
Yeah.
Yeah.
She always had the good best meeting. My daughter had it. But, yeah, I know.
Yes. Twice. This 161, I think.
I
you have
don't
to-
know why, so I would just.
Yeah,
Yeah, just super fast. You don't know it. I mean, it was the same. But that's why I wanted to.
You don't remember. You have like a portion of the. Oh, she.
I usually like to put it on whichever it's, like if there's like this one has two negatives, so by switching that one, I get rid of both of those. It's just nicer that way, but it's up to you.
It's all wrong.
Yes, that kind of thing, like, don't worry.
So my meeting, like,
You just kind of catch the-
around like at 6, not 6, at 7, and we don't.
Yeah, he comes out.
Everything.
Everything.
Like, I said that everything for 3 years, like, next to the 50, and then I was like,
Yeah.
you know, like lecturing teachers, like section 2 and the doc, there's like PDF and then like section 5.
We have to like even specific.
Dude, I haven't been doing
Yeah.
that. Yeah, you know, like.
First thing is what?
I haven't been. We take. Yeah. You want the lecture? Section 5. And like, section 2.
Dude, I found it.
The last part is.
I've been doing that, bro.
See, that's.
That's my stuff, bro. But I've been getting like a 95 or something.
Go back and really. For,
Dude, I haven't been with that. I just.
Ladder 5. And you. What's your.
I think that you.
Those are the ones that I'm going to do whatever, but when you have to see. They could say. I don't know.
Like ours.
It takes a while.
Yeah, right. There's like my photos for that's a lot. Yeah, right.
And he like. Taking like 4 or 5 languages, he was like, yeah, but I was not wrong off. It was 2 books.
So right now.
That's why I was like, dude, what I thought was.
I don't know.
So I get everything.
Never
Like,
has.
for like our last class, I have 5 or 6 people. Like my dad was like, oh, sorry, so this is like. And then I was like, you saw me on that. I was like,
All right, guys, I think I'm gonna go ahead and pick things back up here again. I think almost everybody made it back by now, maybe not quite. But we've got about 20 minutes. Maybe I'll be able to get this done in 10 minutes. Probably dreaming, but we'll see. Again, if I am able to answer some homework questions, great. But if not, I will be around later and can try during office hours as well. But let's take a look at this solution here. This is not acceptable. This is in the form that we've been looking for, right? Everything that we've said so far about the solutions to our non-defective system should look like that, yeah? E to the lambda t times b. And that's exactly what I wrote here. E to the lambda t times b. But because there's an I in this answer, it's not in a real valued form that would be something that we could make sense of. So I'm gonna massage the heck out of this thing and try and shake out a real solution, something that doesn't have an I in it. So we've seen this before a little bit because we had this problem in the last chapter too. So I'm gonna kind of break this down. First of all, I think you can all see that there's an e to the 4t. And that part, so let's just continue our notes right where we left off. The e to the 4t is no big deal to me. I can just take that out. But I also have e to the 2it. Now you might remember in chapter 8 when this happened, when we had like e to the I theta, we had to use the so-called Euler's formula to write it in terms of sines and cosines. And that's exactly what we're going to do here, guys. I'm going to take that e to the 2it. I'm going to write it as cosine of 2t plus I times the sine of 2t. So far what I've taken care of is just the e part. I haven't worked on this vector yet, but the e part, I have e to the 4t, and then I have cosine of 2t plus I times sine of 2t. So I'm not doing so hot so far because I still have the I here, and I haven't even dealt with the vector part. The way you're going to work on the vector is you're going to actually split it into two vectors. The first vector is going to be the vector of the stuff in the vector that does not have I in it at all. So does everybody see that there's a 5 and a -1 that don't have anything to do with I? And then to that, I'm going to add I times the part of the vector that does have I on it. So I see that there's a 2i upstairs, and then in the lower slot, there's no I at all, so I'll put a 0 there. So I can go ahead and do that. Okay, so far so good? So that's the first step. Now, the natural next thing to do is you got sort of something plus something times something plus something. And I'm sure you all know, like if you had a plus b and you wanted to multiply it by c plus d, I'm sure you guys could all multiply that out. What is that called when you do that? In your high school math class, what do they call that? Say it again? FOIL, right? That you FOIL it out. So in this class, we're not going to FOIL it out. We are going to FLOY it out. So it's not FOIL, it's FLOY, and let me show you why and how that works, okay? So first of all, the e to the 4t, so this is what I'm going to call FLOY. E to the 4t is there. And I'm going to make a really big braces because I don't want to get that mixed in with the rest of it. I'm going to go ahead and do the first and the first, right? So cosine of 2t times the vector 5, -1. Okay? And then, so here's the deal. So that's what we normally would call the first. And normally with FOIL, you now do the outers and then the inners and then the last. But I'm going to do FLOY, and I'm going to do the L next. If you look at the last times the last, right? This one times this one. What I like about it is that it has an I times an I. And we all know that I squared is equal to what? -1. I squared is -1. So these two i's will actually cancel out into a minus sine of 2t times the vector 2 and 0. Okay, so that's the last. And I'm going to actually put some nice parentheses around just that part of it. So that's half of my FLOY. And then I'm going to go to the outers and inners. Now, when I do the outer term and the inner term, I will have an I on both of those. I'm going to go ahead and factor that I out. Right? So this is going to be kind of a massive expression. I'm just trying to draw it really big so everybody can see clearly how it's breaking down. There is an I that's going to come on the outer and inner terms, and the outer term is just, you know how FOIL goes. You take the first thing here times the last thing over here. So that's going to be cosine of 2t times 2, 0. And then that's the outers. And then on the inner term, I also have an I, but I've already factored it out. And I'm left with sine of 2t times the vector 5 and -1. So I'm going to put sine of 2t And then I'm gonna put 5 and -1. And this becomes the inners. So this is what I mean when I say in this class, we're going to do Floy instead of FOIL. Now, when I look at that whole big thing, I have almost gotten rid of the I. There is only one place where there is still an I showing up, and it's right here. The rest of it is all good to go. So now here is where we're going to take a little bit on faith. Remember that we have another lambda that we haven't even talked about yet. So far, we've only been working with the 4 plus 2i. At this moment, I could stop and I could say, time out. I'm going to go back to 4 minus 2i and do a null space, write down another whole thing and do a whole nother Floy again. And you know what's going to happen? You're actually going to get the same exact thing that you see here, except with a minus sign between the two terms. And once you've done that, you can, of course, add, subtract, and combine the terms, and you can actually extract 2 real solutions from this expression. We're not gonna, the book goes through all that. We're not going to. I'm just going to extract the solutions for you directly right now. And actually, the beauty of this is, we actually are not ever going to work with the other lambda. I'm going to sweep that under the rug, and I'm just going to get my 2 solutions just from this much work. And what are they? Well, the first one is going to be x1 of t, and this one comes from just this first part. So it will be e to the 4t times cosine of 2t times 5 -1 minus the sine of 2t times 2 and 0. Okay, that's the first solution. That's really just this part here. So that's coming from the first and the last, the F and the L part of the Floy. And then the second solution is going to come from the O and the I part, except without the imaginary number. So I'm still gonna need the e to the 4t, but then I'm just gonna go over here and put the part that's in the parentheses. Cosine of 2t times 2, 0 plus sine of 2t times 5 and -1. Just like that, that's the outers and inners of the Floy. So we have FOILed it out and grouped them up, 2 terms here, 2 terms here. These 2 terms technically still had an I on them, but we're going to just take the faith that if we had worked with the other eigenvalue and done some linear combination of this solution with the one we would get from that one, that we could in fact extract this last part as a second real solution. Guys, what you see here are 2 real solutions. They are real solutions. And I should point out, especially if you like to check the back of the book sometimes, it is possible to compress this answer. You don't need to do this step. What I'm about to show you is optional. But what you can do if you want to make it look a little nicer is you can just compress the part in parentheses into just a top slot and a bottom slot. So if I write across the top slot of everything, I've got a 5 times the cosine of 2t, right? I can do that, and then I've got a minus 2 times the sine of 2t. If you like kind of compressing the expression, that would be fine. The bottom row has a minus on this cosine of 2t, and then there's nothing for the sine part of the second slot. So that would be another way of writing your first solution. And then your second solution, I can do the same thing. E to the 4t, going across the top slot of everybody. The top slot of everything I see, I have cosine of 2t times 2 plus 5 times the sine of 2t. And then on the bottom, I'll have negative sine of 2t. And that would be it. And so my general solution, of course, I maybe won't write the whole thing all the way out here, but the general solution would just be x of t equals c1 times the x1 of t, I'll just write it in shorthand now, plus c2 times x2 of t. This would be the final answer in that form. So that's how you handle imaginary numbers. Question, Edgar.
So the x2 of t comes from the second pair of lambdas.
It comes from the outers and inners of the Floy. I would not worry about the second lambda. So what I'm basically saying is we're gonna sweep that under the rug. We're going to ignore the other eigenvalue. Yeah. So it makes life a little bit nicer to do that. Yeah. Well, what's gonna happen to the feather when I drop it in on this one? Oh my gosh. Can we add a couple more bullet points on our face portrait? I think I'm gonna show you that. Real quick, gotta show you that part. So let's just continue our face portrait summary. So let me just say face portrait continued. And I want to draw the face portrait for this particular one, right? So you can obviously take this one as one of your solutions, and this one as one of your solutions. That's two of them. And of course, then you have all linear combinations of those two. I just want to point out on this solution right here, can we just ignore the e to the 4t for a minute and look at the vector? Would everybody, I'm not going to make this hard. I'm going to make this real easy. I know it looks horrendous. Like actually plotting it, you'd want to use a computer. But let's just get the rough feeling of it. If there was no exponential there, and I just had this vector, which controls the horizontal axis and the vertical axis, would everybody agree that after whatever 2 pi units of time or whatever, this feather would be back in the same spot that it started at time 0? You see the sines and cosines? That is a periodic function that repeats itself every so often. So if there was no e to the 4t in front of it, then when you drop that feather in there, it's just gonna wander around somewhere and end up back at the same spot again. But what does the e to the 4t actually do? That gives this feather some legs and basically causes it to stretch farther away from the origin so that the next time the feather would have been there, it's actually out here. And then the next time it's actually out here. So what actually happens, guys, is this feather will kind of go around in a circle, but it's going always farther and farther away from the origin. So you end up with what's called an unstable spiral. This is a feather that if you drop, and we could go backwards in time and it would kind of look like it's going back towards the origin. And we should draw arrows on this that point outward. Okay, so this is an unstable spiral. And what I really mean by that is, well, so your lambda is A plus or minus BI. You have imaginary eigenvalues here, right? But what actually makes the spiral go outward is the e to the 4t part. That's the stretch factor that takes your vector and makes it always bigger and bigger and bigger. So this is specifically for a greater than 0. Okay, so that's my 4th bullet point in my summary. That would be the 4th bullet point. And then the 5th bullet point, would be, so let me just add this as a bullet point. If lambda is equal to a plus or minus bi with a greater than 0, then we get an unstable spiral. And by the way, if I dropped the feather in a slightly different position, if I dropped the feather here instead, well, this feather is still going to be an unstable spiral, but it's going to interlace with the spiral in black that I already drew. You're never going to see 2 of these feathers crash into each other. That's one of the features of this, even on the face portrait we drew earlier with the saddle, right? None of these, if you start 2 feathers in 2 different places, they will never cross each other. These curves never cross one another, and the same thing is true here, right? So if I come along with, you know, a third feather, so I've got a red marker and I drop it right there, it's also going to interlace with the other spirals that are already there. They will never cross. It has to do with uniqueness of solutions to a system of linear differential equations. You can't have if you had crossing curves, that would mean that, oh, if I have an initial condition, I don't get a unique solution. But usually if I give you an initial condition, then I should be able to solve uniquely for C1 and C2. The constants in my general solution. So you shouldn't expect that these spirals would ever cross each other. The red spiral, the blue spiral, the black spiral, they never cross each other. The other thing that can happen, I'll put it here, guys, is that if lambda is equal to A plus or minus BI, and the A is negative, then what do you suppose we're going to have? It's going to still be a spiral. Like imagine this was e to the negative 4t. So you're still going to get the spiraling behavior, but the spiral is going to be coming inward. It would be what I'm going to call a stable spiral. It's pointed inward. So this is a stable spiral. So on this one, I'm just going to draw a little spiral here with arrows pointing towards the origin. The feather is going to kind of go around in a circle, but it's getting into a tighter and tighter circle, and eventually it would go towards the origin. Yeah. So we have a stable spiral. This one was the unstable spiral that goes outward. And there's one last case, which this last case I think is in the homework for Saturday. The last case is if lambda is just plus or minus BI. In other words, if there is no A part at all. If there was no A part at all, then that just means you don't get the exponential at all. And so all you're getting is the vector piece, which is just made up of sines and cosines that repeat themselves every 2 pi units. This feather will just keep coming back to the same place over and over again. This is referred to as a circle. It's just a circle, and it makes sense because you drop the feather in and it just comes back to the same place again. So there are 6 scenarios here, guys. So my multiple choice matching question just went from 3 to 6. I give you 6 matrices and I've got 6 face portraits. You can match them all up. Yeah.
So the spiral, what makes them is the eye.
Right, the imaginary numbers is what's making that. I always get questions like, how do I know if it's clockwise or counterclockwise? And like, where exactly is it going to cross the axis or whatever? That's getting way too deep into it for what I want, right? I'm not going to be asking you to do that. You can analyze the direction of, like here, I drew the circle like it's counterclockwise, but it could have been clockwise. It depends on the specific problem. So I don't want to get too deep into that here. I just want you to have kind of a surface appreciation of it. Math 310 is where they really hammer into these face portraits. Does anybody have any questions about how this Floy works for these face portraits here? Okay. Well, that's all I wanted to cover today. I have 2 minutes left according to this. How would it be if I was to go down and do those problems on a video in 2 hours and send it to you? Because I know you want to ask me those questions. The 8.7 number 6, it looks horrible because it's got like this tangent function in it and everything. And you get your y1, it's a variation of parameters problem. You get your y1 and your y2 and the Wronski, and it looks just terrible. But actually it simplifies so nice. And it turns out to be a very clean answer at the end of the day. So I would be happy to do that for you. Okay, does that sound okay? So you expect an email from me somewhere between 8:30 to 9 o'clock, and I'll do those 2 problems in the email and just send them out to you. If you have other questions, just stop by my office hours as well. I'll be glad to help you out. That's it for today, guys. Oh, the SOQs, I checked this morning, we are up to 75%. So I need 10 more percent. That means I need about 3 of you who have not filled out the form. You have 4 more days to do it. Try to fill out those SOQs for me. I really appreciate the feedback. All right, guys, have a great rest of your Tuesday. Thank you.